in your lower toolbar on the right.
Okay, so hi everybody, welcome to the February meeting of HAL. And I am happy to see everybody here. Thanks for coming. We have a really interesting speaker tonight and a very timely topic. So without further ado, I think we'll just go ahead and get started. So our agenda tonight is introductions. We'll make some announcements, hear our speaker, and go through our regular what's out in the sky this month, and then go over a few images and sketches, and hopefully have a little bit of time to chat and socialize. So introductions, is there anybody new on online? Any new members here, or anybody want to say hello? Okay, well, I would like to announce that our board, so we had our elections in January, and our board members have, once again, our volunteer board members have stepped up. So I just wanted to acknowledge some of our non-elected HAL members who do a lot of stuff behind the scenes. Ken Saul is our webmaster, who does a tremendous amount of work just to keep the web fresh and current. And Crystal Rowan is our librarian. If you guys are on and feel like saying something, please go ahead. I just want to say thanks for all the stuff that you do. Maybe next month we'll go through, maybe we'll have something a little more formal. I just thought of doing this today. So is Hannah on? Hannah's our outreach person who manages our social media, and she does a great job just keeping Facebook sane, and our Instagram page keeping it updated. So thank you to her too. And then there's Steve Jaworski, who's our Alcor outreach person, and he has agreed to sign up for another year. So anyways, thanks to all those people. A couple of other things, and maybe we'll do that with the board members too next month or something. Other things, we have our scheduled star parties. Now we have our dates. First one is coming up in just a few weeks. In case you're wondering, if you've been to Alpha Ridge lately, the bathrooms are closed and there's porta potties. I talked to the Howard County people today, and they just closed the bathrooms so the pipes wouldn't freeze in the winter. There's nothing wrong with the bathrooms, so I'm going to ask that they open things up certainly before our public star party. Anyways, these are the dates. Keep your eyes open for impromptus as well. The eclipse, we have the eclipse coming up on the 8th, and there's no HAL official event. However, and Phil Whitebloom had a thing at the last minute, so he couldn't join. He had to go take his kid somewhere. But I was going to ask him to get up and at this point and talk to this caravan day. What Phil's plan is to, and this goes against some of the planning advice of our other members, like Jim Johnson, who have given us good advice, like don't travel on the day of the eclipse. But Phil is inclined to just take a tent and look at the weather, draw some circles of different radii from Alpha Ridge, and leave early in the morning and just find a spot. So if you're game for that sort of thing, stand by for announcements on that. Also, I've got some eclipse glasses. The club has a couple hundred pairs of eclipse glasses, and I have a bunch of them here for the folks here at the Robinson Nature. I'll be handing them out. Anyways, stay tuned. Boy, this auto scroll thing is not making me happy.
Yeah, the glasses, by the way, I've been tracking the pricing on that. The availability is starting to disappear a little bit. It is starting to go up in price. I just remember this from the last time. We're now less than 2 months away, basically, and it's going to start really changing quickly.
Okay, so well, we're going to give them. HAL is not going to scalp glasses, but it's good to know that they're in demand. Yeah, we've got 250 pairs, I believe. Okay, well, stay tuned for other special events coming up. I think I have a couple of mentions here. So we have signed up, once again, the Howard Astronomical League will be supporting the Earth Day celebration on the Clarksville Commons. It's an afternoon thing, so if you have a solar scope, we already have, we've got a hydrogen alpha scope, and we need a white light telescope or a C-star if anybody wants to come out. It's not a huge amount of space that we have, mixed amongst the other various vendors, but if you want to come out, it's a great opportunity to just, do some outreach with people who normally wouldn't come out to HAL events. So there'll be more announcements for that on the email chain list. And then,
Pardon me a second.
yes,
Does that say Saturday, April 23rd?
that's what it says. And you know what? I just went to their website. This is an old website. It's my bad.
Okay.
I went and did a screen grab 5 minutes before the meeting. So pay no attention to this date. Thanks for pointing that out. Sorry, everybody.
Yeah,
It's,
it also says 2022.
yeah, well, that should have been
Oh, I can't even see that. Okay.
that should have been
It's an indicator.
an indicator, yeah. Well, stay tuned for the real announcements. This is the just the notification that it's coming, really. Thanks for pointing that out, Eric. And then another event that we haven't done before, but that I'm curious to do, I got the right year on this one, is we've been invited to go down to the mall on this evening and set up, represent HAL. Even if you don't, if the club doesn't do anything official affiliated with the club, then you might want to go down there anyways, because I mean, you can go and set up. If you go down there with the club, they're gonna provide parking and somewhere for us to like pull up and set up our scopes. So details will be forthcoming, whether we do this as a club or if people want to do it as an individual, but that's coming up in June.
Yeah, I did it last year and it's pretty amazing. And last year the weather wasn't very good, but it's really, if you're into astronomy at all, it's worth going to.
You know what, maybe, well, we've got time between now and then, but maybe could I ask that, would you mind giving a little description at a future meeting as to like what it's all about, how it works, and what other things you got to experience there?
I can spend a couple minutes some other time, sure.
Okay, I appreciate that. That would be awesome. Okay, and then this just went out in the email list from Steve Jaworski, our Alcor representative, that he sent an email with all this out there, but I thought I'd include it in case, because the charts will be up on the website if anybody wants to reference it. These are the upcoming star parties. So that was to be Phil was going to give an initial trip report, not an official one with pictures and all that, but he couldn't make it. But we have another person, former President Jim Johnson, HAL member extraordinaire in the room, and Jim, would you be able to say a couple words about this?
Sure. How long you want me to go? About a half hour? Yeah, Winter Star Party was last week. It went from Monday morning to Saturday morning. A little difficult to observe on Saturday night because you had to be out of there by 10 o'clock, and probably if you're somebody that lives way up here, you have to drive a long ways the next day. So kind of put observing out of reach for Saturday night, but great star party. It's down in the Florida Keys. If you're familiar with the Keys, after Marathon, there's a long bridge, and it's the first or second key after you land on the other side of the bridge, and it's right before Big Pine Key. And down there, you're about 15 degrees further south than you are here. That means objects that are low in the sky here are higher in the sky down there, and you have access to a lot of objects that you can't see from up here. So it's really neat in that regard. The weather is great. It's a good break from the weather to get down there. Temperatures are, daytime highs are like low to mid seventies, gets down to mid sixties at night, very comfortable. Pretty breezy though, but unlike here, I find that if you have a surface breeze or a surface wind, you're seeing it's gonna be not good at all. But down there with the laminar airflows, off the water, you can have, higher surface winds and still have good seeing aloft, so that's kind of neat. There's a Boy Scout camp and a Girl Scout camp that the Southern Cross Astronomical Society hosts the star party on. It's the Boy Scout camp is kept very nice. They call them glam tents there. The showers and restrooms are over there. You can hook up to 110 or 120 power. They have that all over the place. They only have tent camping over there. You have to park your car outside of the gate. Is the only drawback with that. The glam tents are kind of semi-permanent, and there's a fee for those. First come, first serve. A lot of people like those. In the Girl Scout camp, a couple of the hurricanes crashed it pretty good, and they have not done any improvements. I know 120 electricity over there, so you probably need a generator. They allow low noise generators, like I think they specify 50 decibels or something like that. But you can tent camp with your gear over there, or you can bring an RV down. That's an extra fee for that. And
How many people are in there?
last year was about 350. This year, I think 275. So this is the first 2 years they've had it after COVID. Mickey's Kitchen is a food truck that provides food service down there. They've done it every year except for last year. Every year it's open except for last year, and this was their last year, so that's kind of the end of a legend there. And that's all I can think of off the top of my head. Any
Are there
questions?
vendors there?
Yeah, there's vendors there. Interestingly enough, Gary Hand showed up as hands-on optics. That's a long story that I won't tell here. And the vendors generally contribute gifts for there's a big drawing. Gosh, I guess there's probably 50 door prizes that they give away. Any other questions?
Well, thanks for that. I
Great
think
start party, long drive.
long drive, got some warm weather, got some good camaraderie.
Yep.
All right, thanks. I think we might have a couple pictures at the next star party from Phil. So without any further ado, I'd like to introduce our speaker, Christine Bernhardt. She is a very accomplished person. Very excited to hear her talk. She is at the University of Maryland, and she is a national STEM education leader. She worked in Congress for a while as a distinguished lecturer. She's obviously got a passion for things space. She's here the night before having some surgery done on her knee. Thank you again for being able to do that. So she has focused on leadership in education, and has developed curricula programs to I'm very curious, maybe we can ask a couple of questions about this high altitude balloon program and the Student Space Symposium and the International Space Camp. She holds masters in space studies and science education, and is doing doctoral research on international astronomy education and teacher learning with a social justice lens. And she's interested in international science education and using Earth and space topics as a gateway for STEM and early learning. So that, without any further ado, would you like to take the screen?
Sure. Can you guys hear me?
Yes.
Perfect. Thank you for having me tonight. I'm Christine, and yes, I am having a major knee surgery tomorrow. And during our talk, my mother is going to be walking in. She just landed. She's been flying for, I think, 16 hours to get here to help me with my recovery. So if you see me like wave to her, it's because I haven't seen her in a while. She's coming in the next couple of minutes. So I am a longtime secondary astronomy education instructor. I've taught at the community college level. I teach teachers, and teaching STEM through the lens of space is something that I'm really passionate about. And you mentioned the high altitude ballooning. This picture that is my background. This was taken by a student GoPro at about 95,000 feet. If you look in the like on over my shoulder, that is actually the moment that the balloon burst, and you can see the little fragments of it. And this little yellow thing over here, that is holding the GPS. We used spot radios. I will never use them again because I almost lost a balloon one time because they went out. And that is our little payload box that has about 15 student experiments in it. So that is the coolest thing I've ever done. And it had nothing to do with me. Students had the idea. They found a grant. All I did was apply for it, and I just kind of got out of their way. So it was very cool. That's not what I'm talking about tonight, though. I am here to talk to you guys about one of my favorite topics, eclipses. Oh, I cannot move my little thing here. There's my mom. So I titled this Total Eclipse at the Heart because I am an 80s baby. Believe it or not, it was very difficult to find a cool picture of this. I had 80s pictures. I had lots of things that ended up looking weird. So here's the album cover. Maybe you'll remember that. Or maybe that will look familiar.
Yes.
Okay. All right. So I did say before we got going that you would need a device to scan things. So if you wouldn't mind scanning this QR code, and then just wait for a sec. It should take you to something called Menti.
Okay, I see.
I got it.
Perfect. I'm going to give you guys a couple more seconds, and then I'm going to get there myself. So if you're online, if you're in person, either way, you should be able to get that. And once you do, that is going to take you to this screen. And if you need that again, you can get here by going to menti.com and using this code so that you can get there as well. And that'll be up on here the whole time. So if you're in, what do you want to learn about eclipses? So you can just put in anything you think. I know some of you guys probably have an immense amount of astronomical knowledge, an astronomical amount of knowledge. And some of you guys may not know as much. For me, I'm a planetary scientist, so I actually know a lot more about our near-Earth environment and planetary surfaces than I do about the astrophysical properties of deep space, because this was where my research was. And I think it's really important for us to learn about our near-Earth environment because this determines our habitability. Cool. So I see two. Why don't they happen more often? Eclipses on Mars. Ooh, whole other topic that I would love to talk about. The Saris cycle. Excellent. Someone has some astronomical knowledge. How many planets could we see during the eclipse? Ooh, very cool. I remember last time being able to see Mars during the day. When is the first written record? Ooh, I hope I can come up with that one off the top of my head. Excellent question. Excellent question. Okay. And I got another for you. Is this going to let me go forward? Nope. All right. And I don't know why this wouldn't let me go forward. Next question. There either is or is not a dark side of the moon. There is or is not.
Not including Pink Floyd's.
Not including Pink Floyd, the best album of all time. Actually, I like Division Bell a little bit better, and you might see a hint of that in the next question.
Nice.
We just moved, and our neighbor blasts Pink Floyd all the time. And first thing he said when we moved in is, "I hope that doesn't bother you." And I said, "Nope, sure doesn't."
Nice.
Okay, so more of you think there is not a dark side of the moon than there is. All right. Next one. Tell me what you have seen. A blood moon, a lunar eclipse, a solar eclipse, the dark side of the moon, and then my Pink Floyd reference, division bell.
Does that
You
include
should be able
partial
to
solar
select as many.
eclipses?
Yes.
Oh, this one's not a check mark. It's like,
Oh, it's not.
a radio,
Sorry.
so you gotta like pick the best one, I think.
Okay. Haha, you got a Pink Floyd fan. Excellent. All right.
I think I have the CD
Very cool.
somewhere up
Oh.
on my rack.
Nice. I used to have the box set in my college dorm room. I catalog. If you don't know what that is, you can Google it. It is the best poster ever made because we used to actually have posters on our dorm room walls. That was my generation. Excellent. So a lot of you guys have seen a solar eclipse. Okay. And last question, at least for a while, this will help me gauge a little bit in some of the terminology I use because I don't want this to be super elementary. How well do you understand the sciences of eclipses? And how well do you understand the science of moon phases? Oh, wow. Okay. Well, I was told to make this like a PBS Nova special. I feel like I should have made this more like a graduate course now.
I think there's a few less of us than normal, and
Okay.
yes, many of us are yeah, I'm probably the lacking of everyone here.
Well, also, the only ones who brought up their phones are, we're the real gung ho members here.
Okay.
We're also
All right.
self-assessing.
Okay, fair. All right. So you can go ahead and put your devices down. You will need them later though, because I like to make learning very interactive, whether I have students who are in K or gray. I always like to make learning something that is actively participatory. So I really love eclipses, and like was said in the introduction to me, one of the things that I'm really interested in is cultural astronomy and being able to connect space to students of all places and times. And something that I find really interesting is the connection of eclipses and ancient history. And one thing I learned when I was traveling in Mexico City, which is Aztec territory. When Cortez came to Mexico City, he actually he was not a conqueror initially. The Aztec like vastly overcame him, but he had an astrologer with him. They didn't call him astronomer, but astrologer with him, who was able to calculate that there was going to be a solar eclipse. And he said, I am so powerful that if you don't give me your gold, I'm going to block out the sun. And then when it happened, people became subservient to him. They had a lot more contact with him. Then you had disease and all of these other things that followed. But eclipses have played a critical role in a lot of different societies. And I feel like that one really had a lot of detrimental effects and is a bit unfortunate. So I asked you the question if there was Dark Side of the Moon, besides being a fantastic album. So one of the things I do with my students to answer that question is we make some observations about some images, and I ask them to avoid the no-brainer questions like it's the moon, it's round, or it's in space, or it's big. So for you guys, I'm going to go through these relatively quickly because it seems like you have a larger astronomical knowledge than some. High schoolers, by the way, go nuts over this photo because in US history, their textbook has this photo. And, this generation, they all know that the flag was faked to look like it was windblown because obviously there's no wind on the moon. So students go nuts over this. I had a student that did an entire project looking at the angle of the shadow in the visor, calculating on that day where the sun would have been to show that this was a faked photo. His math was a bit off, but he went to great lengths to try and show that. So interesting thing that there's such a distrust in science. There's this rising movement of young people that actually like really justify this being an erroneous photo. And it's kind of an unfortunate thing that, you know, the flag really feeds into that. So if you guys were a little younger, didn't have the astronomical knowledge you did, I would go back and I would look at some of these things. So we'd look at a blood moon and talk about why we would see that as red. Or maybe I just ask them if they've seen that, because most people don't realize that they've actually seen a lunar eclipse. They're like, oh yeah, I've seen a blood moon, but have you seen a lunar eclipse? And they say no. But most people you show this photo to will say, oh yeah, I've totally seen that, but they just don't realize that they've seen a lunar eclipse. None of you have seen this photo. Anyone know why?
Because that's the
Or none of you.
side of the moon.
Yes, very good. So you get an A. This is the far side of the moon. So I try and really reframe the speech that my students use. So I don't let them say there is a dark side of the moon unless they are referencing the great album. This is the far side of the moon. So here we have, of course, the near side. And one thing that's interesting is there's so many photos where if we look at the basin at the South Pole, there's so many images that flip that. And when you show students this, and there's just a lot of people that put up these images and don't think about the orientation. Whereas when you really study the geology of the surface, you know where that is. And usually a lot of photos will act, as you guys probably know, it flips that and you have to flip it back. So here's that again. And one of the things we talk about a lot is the process of cratering. And we will get to this in a moment. But students kind of freak out about this. They're like, what the heck? Well, this is just the moon at different times of the year, same portion of sky. And this has a direct role into why we see eclipses the way we do. So we talk about the near side, the far side. And I always ask people, you know, have you seen this side? Has anyone think they've seen this side?
A tiny bit of it during a libration.
Okay. Probably the only time. Or if you were, you know, Apollo 13 astronauts and would have gone around. So in looking at the parts of the lunar surface, we can tell a lot about solar system history. So when we see these portions of the Mare or the Maria and the highlands, these tell us about the geologic surface processes that were happening throughout the moon's history. And from that, we can determine where areas are older, where areas are younger, where we have a lot fewer craters. This is younger. This has been resurfaced by lava flows that happened subsequently after there was impacts, whereas areas that have a high density of craters are much older surfaces. And we can see some secondary craters that form even in the basins of existing craters. So that tells us the superposition and the order of things that happen. So the reason we talk about that, and we talk about some fun facts of the moon when we look at eclipses, is, you know, posing this question of, do you see the dark side of the moon? Is there a dark side of the moon? And I think it's so important for us to be, as scientists and as just citizens of Earth, armed with enough information to dispel a lot of rumors and dispel misconceptions. And there's a lot of students of science and of STEM that don't entirely understand these concepts. So a really fun demo is to have two people facing each other. And if I was with you, I would make you do this. To have two people facing each other and they move around and try and keep the same side facing. And they don't realize it, but they have to shift. And a fun fact is over time, we have slowed the Earth's rotation. So if we take a look at this photo, always the side facing the sun is the illuminated side. Always the side away from the sun is the darkened side. But it's not always the same side. So the far side is a much better way to frame it. But to keep that same side facing us, the moon has to orbit, or it has to rotate. Rotates on its axis, revolves around a primary body. But in order for us to see that same side, they have to be equal. So fun fact there is that a day on the moon and a year on the moon are the same. And it is slowing us as well, and didn't always used to be that way. And it is going to continue to progressively, it is going to slow our rotation as well. So that is one of the reasons that we see the moon the way we see it. So one thing that I think is really fun to do is manipulate these. I created this model so that you can actually move them. So this is a Google slide. And and I think a lot of you guys know this, so if you don't want to do this, you don't have to. But this is a slide. This is a QR code to that slide. And you can shift the positions of these. And at the end, I'm going to give you all of these resources. I have a document that is something that can be really good if you have maybe younger people or people that are asking about the eclipse or asking for information. I just have a really easy take and go flyer with a bunch of things. So if you were to make a copy of that, it will take you to a page where you can manipulate these to be able to see how solar eclipses and lunar eclipses occur. And with this QR code, that's something you can reuse for any of your events as well. So it takes you to something that looks like this. So, and then you can just kind of shift it around, change the order. All right. So looking at eclipses, wow, that is a much more pixelated image than it was when my picture was smaller. Sorry about that. So for us to, look at eclipses, it's important that we talk about the way the moon moves too. So we have two types of eclipses, and they're both happening this year. So the solar eclipse has gotten a lot of attention. I'm a big fan of the lunar eclipses as well, the redheaded stepchild of eclipses. But we actually have one of those coming up in March, so preceding the solar eclipse. So let's not forget about the moon. The moon is important too. So I have, can you guys see the screen?
Yes.
Cool. So geometry is a pretty important factor in talking about eclipses. So the title of my talk is it just a phase or is it geometry? And one thing that is pretty interesting is we don't see any circular orbits anywhere, but the closest to a circle is Earth. So if I were to just change things like that, so Earth is nearly a perfectly circular orbit, but the moon's orbit is elliptical. When we think about comet orbits, they are extremely elliptical. But we can see how, as we change the position of these the primary and secondary bodies, the distances between them, what that does to the shape of the orbit. So it goes from either circularized or much more eccentric. So if we think about the moon and around Earth, Earth has a slightly eccentric orbit. The moon that revolves around us is following that orbit, but the Earth is also then following around the sun. So we have two different orbits that are happening. So in order for us to have a solar eclipse, we have to have a new moon phase. So this is why you see it during the day. One of the questions initially was, what planets will you see out? I'm actually not sure on that. I know in the 2017, you could very clearly see Mars, whereas you wouldn't usually be able to see it during the day. So because this is a new moon, this is happening during the day. Much harder to replicate this scenario because the moon is obviously much smaller than the sun, and you're taking a very small object blocking out something that is very big. A really fun outreach activity to do is to have people take a ping pong ball and a basketball and to try and get it the perfect distance where the ping pong ball blocks the basketball. That's essentially what a solar eclipse is. So when we have that perfect scenario where it's sitting on the node of our ecliptic plane, if you happen to be in that teeny tiny shadow that only covers about 2% of the Earth, you would experience totality. And that's the scenario that we have that's coming up in April. But a lunar eclipse is much easier to create. It takes the moon about 2 hours to pass the umbral shadow of the Earth. And because the moon is so much smaller than Earth, there's such a larger shadow for the moon to pass between. We can see these a lot easier from about half of the planet. So that's why most people have seen a lunar eclipse, whether they know it or not. So if the moon is in the penumbral shadow, it looks different than if it's in the umbral shadow. So when the moon is completely in the shadow of the Earth, we would see a red moon. When it's only partially in the shadow, we would see a grayish moon. And it's interesting to think about wavelengths of light. So we know that red wavelengths of light are much longer than the bluer portions of the spectrum. So when the moon is passing within the shadow, we're essentially seeing these red wavelengths of light and the blue being absorbed. So just a little vocab here. Umbra is comes from, it's related to the word umbrella, so under. And umbra would be the complete shadow. Penumbra is the almost shadow. And these are important, especially when we're talking about solar eclipses, because when you see a partial, you would see the penumbra, and when you see a total, you would be seeing the umbra. So I have a video here. I don't think I'm going to show all of this, but there we go. So you can see that as the moon is passing within the umbral shadow, that it's turning red. And again, we'll be able to see this in March. And we can see that nearly half of the planet is able to view a lunar eclipse during that time. And here we can see what's happening to our red wavelengths of light as they're wrapping around the Earth, coming from the white light of the sun and scattering the blue. I had a student years ago that did a project where he did a time lapse of all of this. And this was way before there was really good time lapse technology.
Can you please play that again? That was so good.
This? Yes. And I will be giving you guys all of these. Oops. Yeah, I thought this was really good as well. So this is from the LRO from NASA. And again, I'm giving you guys links to all of the videos I'm showing. I'll even give you a link to my slideshow.
That video explains why sunsets are red.
Yes, it does. You're absolutely right. And I think that's something that so many people don't entirely understand. And that video like perfectly explains it. And I don't even have the sound on. I've muted it. But there is a really good and easy to understand sound that goes with that. So here we can see that reddening as it's moving across the face of the moon. And then here we can see what I always like to call the chomp being taken out of the sun. My grandma happened to live before she passed away in Salem, Oregon. That's where my mom grew up. So we got to go up there to see the first continental passing of the solar eclipse. And this was such a cool thing. And one thing that I didn't realize, because I'd never seen a solar eclipse before, was this process of that initial bite took a couple of hours. But then that moment of totality was, I think, under 2 minutes. I don't remember the exact time. But this process of moving of the moon moving across the face, because the sun is very large, comparatively, not like it's a big star. But it took a really long time. And the reason we have to wear glasses, just in case you didn't know, is because the sun's rays, it's not that it's stronger. It's that, again, going back to that concept of the like the red light reaching around. It's not that it's stronger, but because the sun is always emitting the same radiation, all you're doing is putting the moon in front of it. But what it allows us to do is then the chromosphere of the sun, which emits UV radiation, becomes much more prominent. So that's why we have to wear the eclipse glasses. But when it's in totality, you don't. You can actually take them off when it's in totality. But if you take them off when it's in this process of going to total, it will you will get a headache and you will see spots. I learned that the hard way. Don't do that. So beautiful picture here where we can see the chromosphere. Also, fun fact, some of the solar eclipses that our early astronomers, Kepler and Galileo, saw, they named this Helios after the god Helios, which is where we get the term helium. That's how we learned that there was helium in the sun, was from solar eclipses. So here is just the shadow taken from ISS of, I think that one's from ISS. Oops. So, thinking about our lunar eclipse where half the planet sees it, and then we just have this shadow passing across, and only if you're in that shadow would you see it. And geometry is important. Like I said before, we don't have a perfectly circular orbit. This is largely exaggerated. We do not have this elliptical of an orbit. Many planets do. Ours is not. Ours is almost zero. Ours is oddly circular for where it is in the solar system, but pretend it was like this. So some orbital positions to know. So when we put Helios in front of or behind something, it means relationship to the sun. But when we're talking about planetary bodies, we use perigee and apogee, but they mean the same thing. So aphelion is away, para is close. So perihelion is when the Earth is close to the sun. Aphelion is when it's further away from the sun. One common misconception, and there was a survey done at Harvard a couple of years ago, and something like 72% of Harvard students got this wrong. They said that the reason it is, summer is hotter than winter is because of that the sun is actually closer in winter. The sun is closer in summer. And you can actually see from this that that is not true. And this blows students' minds. Like, we are actually like 75,000 kilometers closer to the sun in winter than we are in summer. So here again, we can see the orbit of the moon around Earth. So planetary bodies, we use perigee and apogee. When we put an A in front of something, it means the opposite. So perigee is close, apogee is far. Perihelion is close to the sun, aphelion is further. So Helios, because it's the sun. So, Jupiter has a perihelion and aphelion. Jupiter's moons have a perigee and an apogee. These names are important because when we talk about solar eclipses, the position of the moon and the position of Earth determine the eclipse you get. Because when we think about the moon, if you think back to that early picture of the moon I showed you two moons taken from the same place, different times of the year. This is where we get supermoons from. So, and I think this is just such a cool concept, and it's something that maybe as astronomers or scientists we take for granted. But if we think about that, the actual distance of the moon changes by thousands of kilometers. So at perigee, if we think about that distance, just over 2,000 kilometers or 2,000 miles, sorry, I guess I have English units there. I don't usually do that. And apogee, this is a physically smaller portion of the sky. So, from observing that the moon takes up about a half a degree and the sun takes about the same. So, but just think about that for a second. As astronomers, you probably know that, you can hold up your thumb and block out both. But if we think about what that means there has to be some perfect geometry going on here. But because the moon, when it's at apogee, is so much smaller, that means it's not going to block the sun. So because the angular diameter of both of them should be the same, when the moon is at apogee, it is physically smaller. When the Earth is at perigee, aphelion, it is physically smaller. It makes the sun smaller. This is why we get annular eclipses. So when you see an annular eclipse, it doesn't quite cover the entire disk of the sun. That's why. It comes down to the orbital position. So we can see what the angular diameter of the sun looks like due to our position, and the angular diameter of the moon looks like due to the moon's position. All right, and now our eclipse. So I see there's a comment. I don't know if that's for me. Oh, color is the sky during a solar eclipse. I have multiple ideas in my head. Did anyone see the last one and want to answer that?
What color is the sky during the eclipse?
Do you mean like, is it blue?
Grayish.
It's like twilight.
It's like twilight, yeah. The street lights came on where I was. I thought it was.
Is it possible to see constellations?
I didn't see constellations. I thought I would. It wasn't pitch black, because you got to remember, you're just under that shadow. But it's kind of like being in a dark parking lot near a city. Even though you're in darkness, there's light nearby. So yeah, twilight, I think, is a really good way to describe it. But the streetlights where I was at did come on. I did see Mars. Where I was, I saw Venus on the horizon, but Venus was pretty bright. But Mars isn't. I mean, I've never seen Mars during the day, and you could very clearly see it. So yeah, it was like twilight. Good question. This is a video. It's pretty quick, but I gave it to you guys. And I'm not playing the sound, but here you can really, see nicely that teeny tiny shadow, and thinking about how amazing it is to just be able to be in that path. Like, this is why this is, such a bucket list item. It should be a bucket list item for everyone, I think.
It would move even faster if
Can
the
you
Earth
hear it?
weren't also rotating in the same direction. The path of the Umber is known as the path of totality. People in that path see the moon completely block the sun, turning the day into night and revealing the sun's outer atmosphere, the corona. The umbra is over land for just an hour and 40 minutes before moving into the North Atlantic and then skipping off the edge of the Earth.
I'm a big fan of using videos. Oops, not again. There we go. So going back to those definitions we had just looked at, because again, that geometry is important. So perigee is the closest place in orbit to a larger body. Apogee would be the furthest. The ecliptic, as you guys know, if you guys are, doing some sky observing, that's the path where we see the sun on the celestial sphere. The celestial sphere being the projection of our terrestrial sphere onto the sky. One thing I love to tell skeptics, especially as I'm sure you guys have accounted for, I've had a lot of people come to my events, and they're like, when are we going to learn about astrology? Kills me. I die inside a little bit every time. I'm sure you guys do too. And I love being asked the question, well, what about when all the planets are in a line? And I'm like, look up, they are. It's called the ecliptic. I mean, off slightly, but the astronomy question, I love being able to just throw that one out of the water, knock it out of the water. And then nodes are an important component, because if we can only have eclipses when the moon is actually on an orbital crossing node. We'll take a look at that too. So again, taking a look at our types of solar eclipses, and we don't have this for lunar eclipses. A lunar eclipse is a lunar eclipse. It's a partial or it's a total, because remember, we have a larger body blocking out a smaller body. But for solar eclipses, because we have a small body blocking out a really big body, and it depends on the position of all the bodies, we have partial, we have annular, and we have total. And that diamond ring is surrounding totality. So looking at that again, we will be in that teeny tiny path. Well, we are close to it, but if you actually go to Pittsburgh, you can be in that teeny tiny path of totality, whereas lunar is much easier to be able to see. So annular would be and you can actually see in these photos, like the moon is further away in the annular than it is in solar, and obviously not to scale. So again, solar happens to be in a new moon, lunar at full moon. So we see solar during the day, lunar at night. Annular is when the moon is at apogee, so it's not entirely blocking it. And the diamond ring signals the beginning and the end of totality. I love this picture in the upper part, because you can see, so we see the corona in the bottom picture, and the white light is the corona, the only time we can see that. But we can see the pink from the prominences that are coming from the photosphere extending upward into the chromosphere. So it allows us to get a lot of information about the sun. And if you've ever looked at any of the images from the sun from the Soho Observatory or now Parker, it actually does the exact same thing. So we study the sun by mimicking eclipses, which I think is pretty cool. So if you look at, you can go to sohonasa.com, and all of their solar imagery, where they are looking at the outer layers of the sun, they just use a dark disk, block it out, just like an eclipse. So from nature, we've learned the science of how to study it. This is taken from someplace near and dear to my heart, Griffith Observatory. I've taken students here many times. I wrote a whole museum guide to this place. This is really close to where I used to live, and I had a student that put together a time lapse that looked just like this. So I really like this simulation, or this. I'm speeding it up too. And this is from LA. This is right on the hilltop above LA. Pretty cool. Before I moved to the East Coast, there was a lunar eclipse right before I moved, but it was early in the morning, as a lot of them are. And I had my camera. I thought I could see it from the backyard, in my pajamas, in slippers. Couldn't see it from the backyard. So I'm like, oh, I'm going to go to the front yard. Couldn't see it from the front yard. So I decided I'm going to walk down the street. And a neighbor didn't recognize me and started following me in his truck and thought I was a crazy person. And he said, you know, like, can I help you? And I turned around. He's like, oh, Christine. I'm like, it's the lunar eclipse. I'm trying to get a photo. But I ended up having to walk like all around my neighborhood to be able to try and see it. So yeah, my neighbors, I was definitely the talk of the neighborhood for a little bit. Like that crazy space lady. So this is from 2006 across Africa. So this is taken from, I think, ISS. And you can see the path of totality moving across the continent. You can see it pretty well, you know, the Saharan substrate. So it's pretty light. Here's another one. So here you can actually see the satellite. You can see the solar panels from it. So you can see that shadow in the upper portion. So here again, we can see an annular eclipse as it's moving into annularity, amidst it, and then moving out of it again. So initially I had asked you about, you know, moon phases, and we had talked about that a little bit. So when we think about moon phases, these are integral to why we have eclipses. So we have to have these moon phases happening at certain times. The moon has to be in a certain position between us and the sun for us to be able to experience these. But if you think about it, why the heck don't we have them every month? We have a new moon and we have a full moon every month. And that was one of the questions that was asked early on. So we can see that, again, the side facing the sun. So this moon that is in the middle of your screen would be what we would see. And then we have the orbital or omniscient view over here on the left. So we can see that the side and the sun is over on the right. So you can see that even Earth has phases. The side that's facing the sun is going to be illuminated, and always the side away from it is going to be not illuminated. So, you know, that side changes. You know, if we look at the continents, we go into night and dark. The moon does too. It just happens at the same rate as it revolves around us. Oh, sorry, I thought I took that one out. So here is our path for the eclipse that is happening in April. So when I looked at it, the closest for me in DC, I believe, is right outside of Pittsburgh. And you can see that there it is in totality at about 3:20. And the difference between that and Indianapolis is 10 minutes. So if we think about the orbital speed of the Earth, 17,050 miles per hour. I was like, what are my units there? It's moving pretty quick. So, you know, Earth is orbiting really fast, but the moon is orbiting around us as well. And we can see that in our times here. So here's our times again. I have not decided where I'm going to go, y'all. I don't know if I'm even going to be driving at that point. And I'm so bummed because I had plans and I had invites to go to many, many eclipse parties. But I don't know if I'm going to be able to be in a car for 17 hours with a very, very sore knee. So, but I'm going to figure something out. So here we can see the time of totality, and when maximum would happen. And again, I put this in links for all of you, and I'm sure you all know. So in order to answer the question of why the heck we don't have them every month and why we have them when we do, we have to look back again at our moon phases. And we have to think about what a month is. So just like we get days of the week, month is really a month. So we follow a lunar calendar. There used to be societies that followed a solar calendar, and it was actually a little bit more accurate because what we call a month isn't exactly a month. It's actually why we have to have leap years, because our days are not, or our months are not entirely 30 days. They're actually 29 and a half days. So if we think about the time it takes for the moon to just realign back with a distant star, that takes just over 27 days. But the time for it to get back in line with the sun, because Earth has progressed in its orbit, is 29 and a half days, not 30 days. So that's why every 4 years we've got to have a leap year to account for those days. And that's important because someone had mentioned early on in the Menti, the Saros cycle. I think you put Saros, which is actually a bike brand, but it's Saros cycle. The king cycle, because we used to have kings that employed people to be able to predict this because it implied that they would have power over their people. So it's called the king cycle. So we know that every 223 synodic days, and if we go back to that, a synodic would be 29 and a half days. So every 223 synodic periods, or 18 years, 10 to 12 days, depending on whether or not it is a leap year or not, and 8 hours, an eclipse will pass the same place again. Crazy to think about the societies that calculated this 1,000 years ago, 2,000 years ago, with no computers whatsoever. So it's also important to note that the moon's orbit is not perfectly in line with Earth's orbit. It is tilted about 5.1, 5.2 degrees. If it were perfectly on the same plane, like two pieces of paper touching, we would have eclipses every month. So because the moon is not, we can see on the left and the right, when it's at new and full, the shadows don't cross. But in the 12 o'clock and the 6 o'clock position, you can see that they do. So the node is where the orbit crosses on the plane of the ecliptic. So because of that, we have these predictable patterns of eclipses. So you can see that these are exactly 18 years apart. So 18 years from now, we will have this same eclipse again. So early I asked you if this was phases or if it was just a matter of geometry. Probably a lot of this was not news to a lot of you. But what I think is pretty amazing is that it's not just geometry, that it's perfect geometry. The sun is 400 times the moon's diameter, but the sun is also 400 times further than Earth. If you think about setting that up in like a dimensional analysis, you know, and you're unknown, you're known, you're unknown, that makes a perfect equation. But the moon is also receding. So in 570,000 years, we will not have eclipses at all. If you think about the rate your fingernails grow, that's about the rate that the moon is moving away from us every single year. And that's crazy to think about, because that means that not only are we in the perfect place in space to see eclipses, we're the perfect place in time to see eclipses, because our ancient prehistoric ancestors didn't, and our grandkids times 1,000 won't either. So we are the only place that we've observed of all of the planetary bodies that we've now found that have perfect solar eclipses. And I think that that is pretty darn amazing, that it is this perfect, perfect symmetry of geometry. That is all I have for you. If you are interested in these resources, this QR code, I'll come back to that in just a sec, will take you to this, which is a link to two simulations. So lunar phase, ellipses, they'll let you play with that, the one I showed you. An activity that I actually created if you have, it's probably high school level, it wouldn't necessarily be outreach, but to actually calculate the similar triangles. A cool outreach event though is, like I said, the different size balls. Note to self, never say balls with kids, they are spheres. There's also the model eclipses that I showed you, and you have access to those files. I put in a bunch of videos, including the ones that were in this and a couple extra. A couple really cool, more information slides. I really liked these eclipse calendars. This one in particular is this guy here. And I'd never seen this site before, but as I was researching for this presentation, I found this. And I thought this was just really neat, talking about the specificity of all lunar and solar eclipses. So I gave you two, one for lunar, one for solar, for the next like decade. So I thought that that was really neat. And then I gave you the map. So I'll go back to my slides so you can access the QR code, and I can put the link in the chat as well. Any questions?
That is fantastic. Thank you so much.
You're welcome.
We have any questions?
And if that was like really redundant for a lot of you guys, I apologize. And I am no longer on Twitter. I'm sorry that's still on there. You can send me a message and I'll get it, but I refuse to engage anymore. Now that Elon is controlling it.
Would anybody have a question? Anybody got a question? And I am in the chat. I don't have, if somebody online can open up the chat, has 2 screens. If anybody has
And
any
here is
questions.
the link to that.
I'm curious what your dissertation would be about.
Thank you.
So I have 3. I'm doing a 3-paper dissertation. So one that is already in press is I did an international astronomy education survey. So I did I represent the US with the International Astronomical Union, and there are groups all over the world from, I think we're up to like 65 countries or something like that. So we have these groups that report back to the IAU about efforts within their country, and we try and really advance astronomy education initiatives. So through that, there had been a curricular study looking at curricular documents. So like just what was published, what ministries of education said people should know, and they found the intersections of astronomy. But I wanted to know what that actually looked like, because being a teacher myself, what the government says I should teach and what I do teach are not the same. So I wanted to see what people were actually doing. So I did a qualitative study. I had 68 survey participants, and then I did 10 case studies, and I did a thematic analysis. And I was looking at how people used astronomy as a bridge to STEM. I found some amazing examples. And if anyone is interested, I've presented on this a ton of times. So I have a whole couple slides on it. I was looking at the lessons that could be learned because a lot of these were community initiatives. A lot of them were individual initiatives. And then I also looked at how astronomy was a bridge to equity. And in places like Mexico and in Nigeria, astronomy was used to really to foster social mobility in a way that people didn't otherwise have access. And in Nigeria, astronomy was used specifically to get girls in school, because girls don't go to school a lot there. Most of the students there that are unschooled are girls. So they have both their Astronomers Without Borders and the Nigerian Space Agency have this huge initiative to bring space to girls. And there are no telescopes sold in Nigeria. So they have to bring them in. They've never seen a telescope. And they run a space camp, and they pay for students to do the entrance exam for college and for high school graduation, which often exceed people's monthly salary. And it was all through the lens of space. So it was a really, really neat study. It's called Space for All.
That's fantastic.
Yeah, thank you.
I'm just checking out the chat now, and Arjun, that's a good question. I was also having the same question about the color of the sky, so don't apologize for that. Well,
I have one question, if you don't mind, that's related to the moon in general, going back to your earlier topic. As you were showing the near and far side of the moon, one of the topics that I don't hear a lot is the reason for the prevalence of the Mara on the near side and absence on the far side. What is the typical answer you give, or would explain? Obviously, there's likely, I would assume, it has to do with some of the tidal effects of Earth.
Yeah.
But trying to find a simpler explanation for people who ask that.
So what I usually say is, if we look at the density of the crust on the near side and the far side, that justifies the tidal forces hypothesis, because obviously they were impacted at the same rate. But when we started actually being able to do radio waves through the crust, we can see that the near side has such a thinner crust than the far side. So what planetary scientists think is that just like the moon pulls on our rock and gives us, tides of water, we have essentially shifted the core. which is kind of crazy to think about. So instead of the core being in the center of the moon, it's closer to us. But I always like to tell people, you know, that mare means seas. So initially people thought that the moon, that we got our water from the moon, that we gravitationally pulled the water through space, and that those were ancient seabeds, and that the name stuck. So I think it's neat to bring in like the human story to that. But yeah, I try and simplify the tidal forces and the thin crust.
Okay, thank you.
Awesome. Yeah, that's really cool. It's like, I never had thought about that either. Like it's just pulling the soft stuff closer.
Yeah.
Awesome.
And so that, you know, totally changes the geology and then the geochemistry of the near side versus the far side. So you have, you know, a lot more of that regolith versus the rock on the far side.
Well, that was fantastic. Any other questions? While you were doing your presentation, I figured out how to make my slideshow. I'm not as sophisticated as your, you know, dynamic and interactive, but at least my slides won't automatically flip as we go forward. Wayne, basically the thing that was grayed out, it was grayed out because I was in slideshow mode. As soon as I left slideshow mode, I could change it. Anyways, you're welcome to stay on. We're gonna keep the meeting moving. Thank you again. That was really quite fun.
Thank
Christine,
you. Thank you guys
yes.
for having me.
Thank you. You were awesome. Thank you so much.
Yeah, and I'll
Thank you
follow up
guys.
with
Hope to
an
meet you in
email.
person.
Yeah, we'll
Okay.
post the links to all the stuff, and so that all
Okay.
of you can see it, and I'll follow up with you regarding the links. Thank you.
Good luck
Thank you
with your
guys so much.
surgery.
I'm gonna hop out. Thank you. Have a good night.
Surgery.
Bye-bye.
Thank you.
Sorry, guys. My cursor, there's my cursor. Are we back? You guys see that?
Yes.
Man, I feel like such a Luddite after all that super high-tech stuff. Okay, well, let's move on with our next section of the presentation, which is the what's out in the sky. Jim, are you on?
I am.
Go.
All right. So we're getting into kind of like the doldrums here in terms of the planets. Right now, there's a traffic jam before dawn. We've got Mercury, Venus, Mars, and Saturn. They're all really pretty poor targets right now, kind of deep down in that sky glow. So it'd be a little hard. You'd have to have a really good eastern horizon to catch them. Next click. However, Jupiter is still a very good target. It's at its highest right as it emerges from twilight. So that's, you know, get your scope set up ahead of time so that you catch it at its highest point above the atmosphere. And one of the things that you might want to try doing would be, it just had its like northern solstice. And so if you happen to catch, if you observe Jupiter one night and you happen to see one of the moons either transiting, you know, its shadow cutting across, or if you see it like creeping up next to the planet, ready to duck behind it, take a moment and actually, you know, spend like 5 minutes and really do a good little sketch in terms of where you see that moon. And then put it in a drawer somewhere, you know, where you'll hopefully be able to come back to it in about 3 years. If you repeat that with the same moon, what you'll be able to see is how the tilt of Jupiter's axis has shifted. And now that moon is at like a different point on the disk of Jupiter. So just a little activity if you're interested in doing that. Now is a good time since it's just past its northern solstice. Next. The other solar system thing that we've got going on, we do have a few comets out in the sky. Comet 12P Pons Brooks. This is one of the better ones we're going to have this year, unless something amazing crops up. So it's got an orbital period of 71 years, not unlike Halley's. So basically, get out and look at it now on this apparition, or you're not going to see it probably, unless you're quite young. Arjun might get a second shot. But at magnitude 7, and it has a history of outbursts where all of a sudden, like it'll pop some material off and increase in brightness. So I would kind of guess that if you take a nice pair of binoculars out to Alpha Ridge and you scan for it, you might be able to pick it up. This thing's going to get brighter as it heads towards the sun, possibly about 4th magnitude in late March, early April. And for us, it's going to be pretty well positioned up until about early April. So this is one to keep an eye on. It's not going to be spectacular, but you can say, hey, I saw it when it came around for its annual 71-year visit. Next. So since we don't have a whole lot in the solar system, I still kind of consider some of the brighter objects in the sky shallow things. You don't have to have a really dark sky or a really large telescope to look at them. So I thought I'd take a few minutes and just talk about a classic here, which is up in Gemini. First of all, for folks who are not familiar with the constellations or just learning them, now is a good time to pick out Gemini. In the evening, early evening, like around now, you can go out, you can certainly identify Orion if you face south. And Gemini's up to the upper right of Orion. And on the 5th of this month, I'm sorry, the 20th of this month, the moon will actually be very close to Pollux. Pollux and Castor are the two bright stars in Gemini, and that's why we call it the twins. They're about 5 degrees apart, roughly, which I think is about your fist extended, maybe not quite. All right, next slide. So Castor is interesting in that it is actually a 6-star system. So with double stars, we name the components alphabetically. So the brightest one in the system is called A, the next brightest is B, and then so on and so forth. So if you were to put a telescope with, and it doesn't have to be a particularly large telescope, but if you put a telescope on Castor and you crank up the magnification a bit, like maybe 200, 300, you'll see that it is actually a double star. So what looks like a single star to your eye is actually going to split into 2 very close components. The brighter one is going to be 2nd magnitude. The slightly dimmer one is 3rd magnitude. And remember that magnitudes are a logarithmic scale. So a unit of magnitude difference translates out, I think, to about 5 times. So the secondary star is about 5 times dimmer than the primary. But that's kind of neat to, in your telescope, see this very, very close double star. There is a 3rd one, Castor C, which most people haven't paid, you usually don't pay much attention to it, that actually is also part of this system. And that's a red dwarf. It's much dimmer at close to 10th magnitude. So you'd probably need a slightly larger telescope to pick up on that, but still not, extremely large. I think a 4 to 6 inch should be able to do that. And it's about 73 arc seconds. So it's about 12 times further away than that distance when you split A and B of Castor. And an interesting fact is that this is actually a pair of red dwarfs that are in orbit. And just like the star Algol, which eclipses, this also eclipses, although the magnitude of the eclipse is not nearly as significant as Algol's. I think it goes from like 9.2 to 9.8. And you can see on the bottom here, Castor A and Castor B are both much larger than our own sun. However, the red dwarfs, of course, being small stars with long lifespans, they're going to be reddish and a lot smaller than our sun. Next.
Did you say what size telescope is good to be able to split A and B?
I think even a 2-inch telescope with some magnification on it would do it.
Okay,
I would think anything larger than a 3-inch should definitely be up to doing it.
great.
So the other interesting thing is that about half a century ago, back in the 60s and 70s, the distance between A and B was only 2 arcseconds. It was a much tougher double star to split back then. And if you look at the orbit there in the diagram, you can see that we are on the upswing here, and we're going to be gradually increasing until it's going to be probably about 6 to 7 arcseconds towards the end of this century. And then it's going to gradually start to close back up again. And one of the things when you're talking about double stars, if you're not familiar with it, is that they will list the PA, which is the position angle. So basically, if you go due north, and then like a hands of a clock, you start going around to the east, due east is 90 degrees, due south is 180, due west is 270. So in your eyepiece, basically it's almost a northeast angle. If you look at the brightest star and then the angle it makes to its slightly dimmer companion here, it's going to be about 45 degrees. But back in the 60s and 70s, it was closer to 90 degrees. So it's one of these star systems that, although it's got a long period of 467 years, you can see changes over, a couple generations. Click. The other thing, it's kind of neat to do a little bit of the historical context of something like Castor. It is one of the very first true physical binaries that we were able to discern. Herschel in 1803 basically kind of postulated that. And it was based on these changes that we were just talking about. You can see it change in its PA as well as its distance. And so it's really one of the very first examples that we had back in the 17th century that Newton's laws about gravitation applied not just here locally on Earth, but applied out among the stars as well. That image there, by the way, that's a sketch by Richard Orr, who is one of the HAL members and just does a phenomenal job. Here is his sketch of Castor A and B, and then the red dwarf C. You can see, as I was saying, it's about 12 times further out. And, it's definitely doable if you have like a 4-inch telescope or better. Why not try giving this a shot? Try to split Castor and see if you can pick up the red dwarf as well. It's one of the classics.
Nice. I can't tell from in the room here, but did he draw the C is it much redder on your screen?
It shows much dimmer. He's got A is definitely a larger round orb, B is a little bit less.
Did he draw it reddish?
No, I don't think he did color in this.
Okay. You ready? Is that all?
That's
great.
it.
Thank you. That was awesome.
You're
Even
welcome.
when the shallow skies are not interesting, you come up with interesting stuff to talk about. Thanks, Jim.
You're welcome.
Wayne, you on?
Yeah, I'm here. So in What's Up in Space this month, I want to talk about a new paper that's been put out on the archive system for astronomy papers. It has been accepted to the Astrophysical Journal's letters, but it hasn't actually been published yet. But it's some JWST observation of white dwarf exoplanets. So basically, the authors used JWST's MIRI mid-infrared instrument to observe a couple of white dwarf stars. looking to see, among other things, if they had any exoplanets. Both of the white dwarfs they looked at are metal rich white dwarfs. And I want to talk about that for a minute because frankly, it didn't mean much to me when I saw it, but but then I looked up at more information and it became much more interesting. So first of all, what do we mean by metal rich? Well, you're all probably familiar with the periodic table of the elements, you know, that horrible table that they put up in chemistry that shows all the elements with hydrogen on the upper left and helium on the upper right and everything else down below and between. Okay, part of that diagram, that table, is the elements are considered metals because they're good conductors of electricity. And so that's the formal definition of a metal. Well, astronomers have made the periodic table very, very much more simple, much simpler. We have hydrogen, helium, and metals. So basically, any element that has an atomic number bigger than helium is tossed into metals. And the reason we do that is because in most astronomical settings, everything more massive than helium is just such a low component by number or mass of the material that it makes very, very little difference. If you take care of hydrogen and helium, you've taken care of more than 99% of the object. So it's easy to just dump them all together and call them metals. Okay, so that's what a metal-rich star is it's a star that shows evidence in its atmosphere of having elements heavier than hydrogen or helium in it. Okay, but most white dwarfs are considered to have pure hydrogen atmospheres, primarily because the gravitational field in a white dwarf's atmosphere is so strong that it pulls all those heavier elements down to toward the center of the star and gets them out of the atmosphere so we can't directly observe them with spectroscopy. So the fact that they're metal rich is actually a bit unusual. So about 25 to 50%, maybe. I saw another paper that said 25 to 33% of white dwarfs have metals in the atmosphere that we can observe. And so the presence of these heavy elements is an indication that something is going on to cause the metals, the heavier elements, to be present in the atmosphere when normally you would expect them not to be. And the current hypothesis is that the metals are continuously accreting onto the star from material orbiting it. And one possible source of that material is from asteroids and comets in orbit around the white dwarf, whose orbits have been disrupted by gravitational interactions with giant planets. Meaning, if you look at a metal-rich star, if the hypothesis for the presence of the metals is correct, there are likely to be giant planets, Jupiter-sized or bigger planets. So there's a good place to go looking for exoplanets. Okay, so you can see so that's why I highlighted that they're both metal-rich stars. It's important for actually finding exoplanets. These two white dwarf stars are faint by our visual observation standards. They're very bright for JWST standards. They have near-infrared magnitudes of 12.3 and 13.5. They have masses that are estimated to be about 0.6 times the mass of the sun and 0.7 times the mass of the sun. But remember, white dwarf stars are evolved stars. And back when they were on the main sequence, they had masses about 1.3 times the mass of the sun and 2.5 times the mass of the sun. This is obviously obtained through modeling of stellar evolution. So it depends a little bit on your model. The estimated ages of these white dwarfs are 5.3 billion years and 1.6 billion years. And I've put the numbers here in the same order. So the magnitude 12.3 is the 0.6 solar mass, 5.3 million year star. And similarly for the other one. So if you notice the main sequence mass of the 1.3 mass solar mass star is older than the 2.5 solar mass star, which is an artifact of the fact that more massive stars evolve more quickly than low mass stars. So the more massive star has reached the white dwarf stage after less than 1.6 billion years, and the 1.3 mass solar mass star has a age of 5.6. So the lower mass star is older. No. The stars are at distances of 10.43 parsecs and 16.18 parsecs from the Gaia catalog. That means they're pretty close to the sun, which means that if there's an exoplanet, it will be sufficiently away from the star that we might actually have a chance to actually observe it. Okay, so they made their observations of the white dwarfs, and in order to identify the white dwarfs, they subtracted a point spread function from the white dwarf. So a point spread function literally means if I have an optical system, what does a point look like what does the image of a point look like? And so they measured the point spread function by another method. Let's see, I can get that on the next page. So they determined the point spread function, they subtracted it, and if there was another object close to the white dwarf, then it would not be subtracted out and it would become visible. And we'll see that in just a moment. And by doing this, they determined that there were planets at 1.1 arc seconds from the brighter of the two stars and 2.1 arc seconds away from the fainter of the two stars. So they think they found a couple of exoplanets. They then used photometry. They observed in multiple filters ranging from 5.6 microns to 21 microns. And they use those photometric measurements then to estimate the planet masses by comparison with, again, models of giant planets. And so what do they expect from the models? They expect the exoplanets to increase in brightness with longer wavelengths. Remember, we're looking in the mid-infrared, so we're primarily seeing light that's actually being emitted by the planet because it's got a non-zero temperature. So we're actually seeing the planets glowing from their light rather than the reflected light from the white dwarf. And so we expect their brightness to increase with longer wavelengths because as you have a cool body, their peak of their brightness, their spectral energy distribution is at longer wavelengths. And the shape of that energy distribution depends on the mass of the planet because of the way the planet would be cooling. Okay, next slide. Next slide, Victor.
Sorry.
That's all right. Okay, so here's the good stuff. So the figure there shows the JWST observations. This is the top row is the white dwarf 1202-232, and the lower three panels are the white dwarf 2105-82. And the white dwarf in the left-hand side shows the left-hand panel in for each of the objects shows the observations, and the bright object in the center is the white dwarf itself, and you can see the beginnings of the point spread function, those little dots around the white dwarf. That's part of the JWST point spread function. So the left-hand panel shows the actual observations. The middle panel on each row shows the PSF subtracted white dwarf. So they took a PSF from another observation of a different white dwarf that was in the same spot on the detector. It's important because the point spread function changes across the detector. So to get a good subtraction, they have to find a white dwarf that's at the same position. And so they scaled the modeled white point spread function and subtracted it from this observation, and you can see it, the star went away, and its position is located by the star symbol on the middle panel. And in the upper panel just below and slightly to the left, there's a slight brightening that's left there. It's clearly real. It's not just a noise artifact, because you can look at the rest of the image and see what the noise looks like. So it's clearly real. And in the lower panel, lower set of images, the middle panel, the residual image is to the upper right from the star. And those two little brightenings are their suspected exoplanets. And just to be sure that their modeling is correct, that this is a planet and not, say, for instance, a background galaxy, they then, on the right hand of the panels, they have scaled that white dwarf PSF again to match the brightness of the planet, and they've subtracted that from the image, and you can see the exoplanet candidates have disappeared completely. That shows that the object that they see, that residual object that's an exoplanet candidate, is actually a point source. It's not an extended source like a faint background galaxy, which
Awesome.
which lends credence to the idea that they're actually exoplanets. So to the right of the figure, I have put in what they estimate the parameters to be. The upper exoplanet is projected separation. They don't know anything about the orbits. They don't know what its orbital size is, but it's currently projected to be about 11.5 astronomical units from the white dwarf. And on their modeling, they estimate it to be 1 to 7 Jupiter masses. And the lower white dwarf, the separation, again, just projected. They don't have any information about the orbit, but the projected distance is 34.6 astronomical units, and they estimate the mass to be 1 to 2 Jupiter masses. So they intend to take further observations to definitely exclude background sources. They can do that by these observing the proper motion. If it's a planet and has a many year period, like a large Jupiter at those kinds of distances from their sub-solar mass star would have, they can just see in just literally a few years, they can see if the white dwarf and the suspected exoplanet have the same proper motion. Okay, so that would definitely exclude it as a background source. If the exoplanet stays stationary and the white dwarf moves, then hey, it must be a background source. Okay, and so they're going to take those observations, and then that'll help them further constrain the models of cool giant exoplanets.
Wow.
So I thought this was interesting, mostly because they observations like these can teach us about the survivability of planetary systems through the giant phases of stellar evolution, for instance, right? So it tells us how, that these planets, if they're really planets, were much farther out than the star reached in its red giant phase. They can also, excuse me, they can also provide physical constraints on giant cool giant planets, excuse me, and also about the variety of cool giant planets. And they also provide evidence for what they call the pollution hypothesis for the presence of metals in white dwarf atmospheres. So I thought this was pretty exciting, and that's why I thought I'd share it with you.
It is. It's very cool. And they're close enough that, pretty soon we'll be able to just take a hop, skip, and a jump over there and look for ourselves.
They're
cool.
pretty close to us.
Wayne, one of the things that occurs to me is that typically finding exoplanets depends on either the transit method or the gravitational pull on the primary star. This is remarkable in that we're actually seeing the exoplanet itself. Is that correct? I mean,
yes, I do want to stress that these are candidates. They've got basically one observation of them. They need to make additional observations to confirm that they are actually exoplanets. But yeah, we've directly imaged exoplanets before. Most of the time they're associated with young stellar systems. You are correct that we usually find exoplanets by transits or by watching the spectroscopic, the changing redshift, basically the periodic redshift. of the star. But we have directly imaged exoplanets before, but they're typically in young systems, often actually still having their protoplanetary disk in around. So the planet's actually still in a very young system. These are planets in very old systems, right?
Right.
White dwarfs are very old, so
Very
so
interesting.
that
Yeah.
also makes it important and unique.
Very cool. Thanks
Thank
for sharing. Any other questions for Jim or Wayne? If not, then I'll move into Astro Images. Here is the California Nebula from Chris. Is Chris on? I'm not sure what his capture details are, but it's a very nice. I think it's the regular light filter, regular UV-IR filter. Steve, are you on?
Yes, I am. I added the Optolong Ultimate filter to my collection of filters, and this was one of the first sets of images I got. This is a mosaic of 3 sections taken at f2 with the hyperstar, and I was pretty pleased at how it did. I thought it made a really nice image. These very narrow band double band filters aren't supposed to be very good on short focal length telescopes, but I was pretty happy with the result here.
Yeah, that's fantastic. How much time were you?
Oh dear, let's see. I think it's a stack of 12 frames at what, 30 seconds, something like that.
Yeah, it doesn't take at f2. It doesn't take that much.
That's right. No, the f2 is really fast. I don't have to guide most of the time.
Wow, fantastic.
Really
Yeah.
sharp image.
Yeah, it's beautiful.
Yeah.
And then you had another interesting thing.
Yeah, I had just seen the announcement that they had examined results from the SOFIA, the Stratospheric Observatory, which has been discontinued, but they detected water on 2 asteroids. So I looked at my collection of the first 21 asteroids, 1 through 21 that I've got. And these are the 2 that they detected water on. So I've got pictures of the 2 asteroids.
Nice.
That was just for fun. Yeah.
So
Yeah.
do you have special software that helps you identify what the asteroids? I mean, you see something moving in your images. How did you identify it as being?
Oh, I look up the coordinates, the ephemeris, but this was, let's see, Iris that's an hour's worth of observations, so it doesn't take very long to see that it's moving. If you get anywhere near it, you can see it, and Massalia was through 2.5 hours, so you can see they move right along.
Nice.
So it's in an evening, take a shot every half hour and you'll see it.
But you knew what you were looking for when you were.
Oh yeah.
Yeah.
I had the coordinates.
Yeah, nice.
I used let's see, probably Carte-Ciel for those.
Nice.
Yeah.
I have long exposure images of things that are in the celestial, like say the Pleiades or something. And I can see all sorts of things moving, but gosh, I have no idea what they are. There's a lot of them. It's good that you researched it and knew what you were looking for.
Well,
very, very nice. Thank you.
Yeah, this is going the other
JPL,
way. Knowing what
JPL has a really good site called the Horizons system.
Yes.
That you can
right.
look for. You can specify a region of sky, and it will tell you what objects, solar system objects, are in that region of sky, and so that's very helpful.
Cool. And it's too bad our speaker wasn't able to stay on because I think she had some work or she did something on the SOFIA mission, so that would have been of interest to her. Anyways, and then we have Ada Carine. Speaking of the Winter Star Party, we have Jim here.
Yeah, this image was taken during the Winter Star Party. This is an object that's not accessible from up here in the, at our latitude. Even down there in the Keys, 15 degrees farther south, it only gets about 5.5 degrees above the horizon, at culmination. I had hoped to image it over 3 nights. The first night I was going to do 2 hours of luminance, and then the next 2 nights get roughly an hour, maybe a little more of RG&B. But all I got was because of the horizon needing to be completely clear, I got 21 minutes on that the first night, and that's all I ever got, just a brief opportunity. And that's with an f/5.4 scope. At 21 minutes, Eta Carina is a star forming region that emits in excited hydrogen wavelengths that appears red in real life, but that's just a stack of 21 60-second luminous images.
That's amazing for 5 degrees off the horizon, 21 minutes. That's really amazing.
Nice image.
Yeah.
Up in the upper left corner is the Gem star cluster, way up in the upper left. And coming back in a little bit is the so that's the Gem cluster. Come back to the lower, nope, to the lower right of the Gem cluster.
Oh,
There's 2 bright stars come down, come back toward the center a little bit, right there. Right, the big bright thing there. That's a named nebula, and I can't think of it off the top
it's
of my
not
head.
the running chicken, is it?
Not the running chicken, no.
That one cracks. That's near there.
Okay,
It's near the Eta Carina. There's something called the running chicken nebula. Huh, cool. We'll have to look at it. Yeah, that's amazing for 21 minutes. Jared, are you on? Well, let me ask, Mark, are you on? These are the same object. This is the object of the month for the HAL Discord group. I'm forgetting the name of this thing.
It's the Jellyfish Nebula.
Thank you. So this, Jared told me, was processed in SHO, which is, the normal palette that the Hubble palette uses. And he didn't do anything to, a lot of times when you do a Hubble palette picture, at least me, and from what I've gathered, I'm starting to do some narrowband imaging. A lot of times you kind of really de-emphasize the green. So it's SHO, sulfur, hydrogen, oxygen. Hydrogen tends to be the brightest emitter. And so when you first form your image in the SHO, it's often very, very green. And so it's not uncommon to de-emphasize that green and or blend it, or but he didn't do that at all in this image. I guess I wish he was on to tell us, but I think he indicated in the Discord that he didn't do very much of the green removal. So that really gives you a picture of what's sulfur and what's hydrogen in this it's pretty telling. I think it's a really cool image. I personally have renamed it the Barfing Frog Nebula, but anyways, that's really
has sort of a 3-dimensional kind of a quality, with the brighter object closer than the further one.
Yeah, for sure, too. It's a gorgeous shot. And this is the same image from Mark Parsons.
I see. Okay.
Obviously a longer focal length,
Yeah.
and looks like a Newtonian scope with the
Okay, right. Star diffraction.
yeah. And there's also some 3-dimensionality here too. It's a pretty image. Anyways, that's all I had for images. Since we have about 15 minutes, in terms of the solar eclipse, there's some practical items. Do you want to just go over these,
I'll
Jim?
go over them real brief. I
Real
think
brief.
Christine pretty much hit everything I got up there. Most important thing I'd want to stress is eye and sensor safety when the sun's in the partial or the eclipse is in the partial phases. You got to be covered up with proper filtration, protect your sensors in your eyes. Like Christine said, when you get the totality, definitely take the filter off, and that's the only way that you're going to see the corona, which is what you came for. Being in the path of totality, if you're outside of the path, even just a little, at best, you're going to get a partial eclipse. Make sure that you know where the path is and what time you need to be there. And the deeper into the path towards the center line you are, the longer the duration. So make sure that you understand the map and where you need to be and what time. The place that I'm going is a campground on the Ohio-Indiana border. And I went out there to scout places in last April and found this place. They did right on the path, right on the center of the path. They didn't know anything about it, hadn't heard anything from anybody. And I called to confirm my reservation 2 weeks ago, and they are booked up.
Yeah.
The people are mobbing that place. So I assume that venues are starting to book quickly all along the path. So get your plans made. And I'm sorry,
Houston Woods,
I'm sorry.
was that Houston Woods?
Didn't hear.
There was a campground.
It was Wildcat Wood
Okay.
near Greenville, Ohio. In Union City, it's on the Ohio-Indiana border. Millions will be traveling. My recommendation is plan to be at your observing location hours before totality, but you might not be able to move to get in. Christine alluded to this. Imaging might be best left for the pros. You don't want to be fiddling with equipment and miss the eclipse. Weather, some people will choose a location to go there and stay there no matter what. Others may have the ability to move to a place that's out from under the clouds. So just be aware of the weather. Observing plan, know what those objects are that's going to be in the sky during totality, and check those out. There's observables on the ground and then other observables in the sky. Just have a list and look for them. 2 presentations that I've done on the eclipse are there at the link if you need more information, and certainly contact me. If I should have put my email address up there, contact me through whatever way you can, and be glad to try to answer questions for you or get the answers.
You can always post something to the HAL and then you'll reply.
Okay.
Yeah. All right, well, thank you. I'm gonna stop the share, and I think I'm also going to stop the recording. If we still have about 10 minutes, if anybody wants, I think we can stay on and shoot the breeze a little bit. I'm gonna stop recording, and then maybe we can talk a little bit more before we have to leave the Robinson here.
Quick question on the eclipse. Are there any maps that anyone has seen about the areas on the outside of the path of totality where there'll be a decent partial visibility, or how far that extends out from the side?
The partial phase is visible from well outside of the path of totality. Even here in Maryland, you'll be able to see it. I can't remember what the percent is, but it's pretty far up there. What's that?
There's at least like 75.
Yeah, something way up there.
75 block.
35% block, yeah.
Wow.
It's going over the Appalachians. We're not that far from totality.
It won't make much difference. It'll still be very bright.
Oh, yeah, but
Yeah, when you're not in the totality, I guess you can look at the shadows on the ground and
Right.
and I think one time I made a pinhole camera and could
Yeah.
see the little
Yeah.
arc.
Last eclipse, somebody took a colander that's got lots of little circles
Yeah.
and had many images of the eclipse that was done right here in Maryland. And somebody took a straw hat that has many holes in it, did the same thing. You can look at.
That's all with a Ritz cracker.
I'm sorry?
It's all with a Ritz cracker.
Okay, that's a good
Holes in
one.
the-
If you look in the shadow of trees where the sun goes through the little spaces between the leaves, you'll see lots of, images of the eclipse.
You
Nice.
flip binoculars around, you can
Yeah,
get a decent sized image on the ground.
I'm gonna
yeah,
stop the recording.
I just